Welcome back to another explainer. Look, if you're gearing up for your Cambridge exams, you know there is zero margin for error. Every calculation has to be perfect, kind of like a space mission getting ready for launch. And if you're tired of just memorizing math formulas without actually understanding why they work, well, you're in the exact right place. Today, we're taking a visual journey into calculating circle properties, specifically mastering arc lengths and sector areas. By the end of our time together, you won't need to rely on rote memorization because you're going to clearly see the geometric logic behind the math.
Okay, let's dive right into this. Here is our roadmap for today. First, anatomy of a circle. Second, calculating arc lengths. Third, finding the sector area. Fourth, working the formulas backwards. And finally, real-world applications.
Section 1. Anatomy of a circle. Defining the pieces. Right. Before we touch any math or crunch any numbers, we absolutely must visually anchor our terminology. Let's look at our first definition, an arc. An arc is simply a part of the circumference of a circle between two radii. If you think of a circle like a freshly baked pizza, the arc is strictly the crust on the outer edge, literally nothing more.
Next up is a sector. A sector is the region of a circle enclosed by two radii and an arc. Now the distinction here is absolutely crucial. While the arc is just that outer crust, the sector is the entire two-dimensional space inside that slice. It's the cheese, the sauce, and everything in between the center point and the edge.
So, what happens when you cut a slice out of a circle? You actually create two slices. And this brilliantly illustrates the contrast between minor and major. The minor arc or sector is the smaller piece, the literal slice you take out. The major arc or sector is the remaining larger piece. What's left in the box? I point this out because it's an incredibly common place for students to lose simple marks. Always read the question carefully to see whether a problem is asking for the minor or major piece.
And for those of you specifically following the course syllabus, take a deep breath. As this quote, straight from the syllabus notes, students following the course syllabus are only expected to work with sectors where the angle is a factor of 360 degrees. This is great news, guys. It means you're going to be dealing with clean, manageable fractions, allowing you to focus entirely on the core concepts rather than getting bogged down by messy decimals.
Moving on to Section 2. Calculating arc lengths. The proportionality principle. The crucial point here is that these formulas aren't magic. They are grounded entirely in simple proportion. Take a look at this donut chart. We have an 80-degree slice and a 280-degree slice. The absolute core anchor for all our calculations today is this. The size of any arc or sector is always determined by its angle out of the full 360 degrees of a circle. It's just a fraction. An 80-degree slice is simply 80 over 360 of the whole thing.
Which brings us right to the actual formula. Arc length equals theta over 360 multiplied by 2 pi r. Theta is just a fancy symbol for our angle. Notice how cleanly we can break this down. Theta over 360 is exactly the fraction of the circle we just talked about, and 2 pi r, well, that's just the standard formula for the circumference of a whole circle. You find the length of the whole crust and then simply multiply it by the fraction you actually want. Simple, right? Oh, and before we keep going, make sure to subscribe to our YouTube channel, AC Exams, at acexams_IGCSE to excel in your Cambridge examinations. Hit that button so you don't miss out.
Okay, Section 3. Finding the sector area. Applying the same logic. If you understood that last calculation, this next concept is going to be completely effortless. Take a look at the area formula. Area of a sector equals theta over 360 multiplied by pi r squared. See what we did there? We kept the exact same fraction at the front, the angle over 360, because we still just want that specific proportion of the circle. But since we want the 2D space now, the actual area, we multiply our fraction by pi r squared, which you'll instantly recognize as the standard area formula for a whole circle. And this brilliantly illustrates the connection. Look at them side by side. The arc length formula uses theta over 360 times 2 pi r. The sector area formula uses theta over 360 times pi r squared. The front half is completely identical. You're literally just swapping out the circumference formula for the area formula at the end, depending entirely on whether you want the length of the edge or the space inside.
Let's keep the momentum going. Section 4. Working the formulas backwards, finding the missing link.
Now that we know how the machine works forward, let's level up. We know how to find the area if we have the radius, but what if we only have the area and the angle and we need to find the radius? This requires a little bit of algebraic gymnastics, but if we stay organized, it's entirely manageable.
Let's look at a worked example directly from our source material. The trick here is to cleanly separate what we know from what we need to find. In our given variables column, we know the area is 50 square centimeters and the angle, theta, is 30 degrees. Our target variable is the radius, r. Setting up your data visually like this is a game changer because it prevents you from getting lost halfway through the math.
Let's walk through the scaffolding of this algebraic manipulation step by step so we completely avoid cognitive overload. Step 1. Set up the equation. Plug in what we know. 50 equals 30 over 360 times pi times r squared. Step 2. We need to isolate r squared, so we multiply both sides by 360 and divide by 30 and pi. That gives us 50 times 360 divided by 30 times pi equals r squared. Step 3. Calculate that value, then take the square root to solve for r. And boom, we get r equals 13.8 centimeters. By moving the pieces systematically, the complex becomes incredibly straightforward. Zero margin for error.
Finally, Section 5, Real-World Applications, Compound Shapes and Sprinklers.
Let's see how this builds into real-world applications. Compound scenarios test whether you can combine multiple simple concepts. Take a look at the parameters from this rotating sprinkler problem. We have a sprinkler placed in the corner of a rectangular garden. The garden's long side is 12 meters. The sprinkler's reach, which effectively acts as our radius, is 8 meters, and it rotates through an angle of 30 degrees.
Now here's the trick. The framing question isn't what is the watered area. The question is, how do we calculate the area of the garden not being watered? Remember, in real-world exam applications, you're very often asked for the leftover area or the major sector. You must read the question carefully to pinpoint your actual target.
So here is our strategic roadmap to solve it. Step 1. Find the total area of the garden by calculating the standard area of the rectangle. Step 2. Find the watered sector area using our new proportional formula, 30 over 360 times pi times 8 squared. Step 3. The final, crucial move, subtract that watered sector area from the total garden area. This proves perfectly that complex, multi-layered questions aren't actually hard at all. They're really just a few simple proportional steps chained together.
We'll wrap up with this overarching takeaway. Mathematics isn't just about memorizing formulas. It's about seeing the proportional relationships between the pieces and the whole. Once you see the fraction, you see the solution. So, I'll leave you with a question to ponder. Next time you look at a curved object out in the real world, a pie, a folding fan, a curved doorway, what proportions do you see? Thanks for joining me for this explainer, and keep looking for the math all around you. And remember, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Drop a comment below with your target grade and let us know what you're working on next. See you next time.